Hey, welcome to our continuing journey in geometry. In this presentation we're going to look at areas of triangles, sectors and segments. You might say, hey, I already know how to find the area of a triangle. It's a half base times height, and we just find the height. There it is, or in that case there it is, or it's an actual side in that triangle, and away we go. Well, I want to pose a problem to you, budding young mathematician. That's a good comment, but what about this triangle? Do we actually have to draw the altitude in and find it? Or is it possible to find the area of this triangle knowing only the sides and the angles without actually having to calculate the altitude or the height? That's our challenge. And just look at the notation in this triangle. Do you remember, or you might not have seen it before, if you have a point A, the side opposite is little a. If you have a point B, the side opposite is little b. Point C, the side opposite is little c. So that's a notation we use in geometry. So I want you to take that on board as we go into finding whether we can get the area of this triangle without actually calculating the height and going back to this old formula up here. All right, what's a sector then? I wonder if you can do that. A sector is like a piece of pie. How would you calculate that area? Well, I don't know. What about I want you to think about this as we go along. This is actually a fraction of the whole circle, isn't it? It's a fraction of the whole circle. And wow, we know the area of the whole circle. It's this. So can we work out what fraction we got in that piece of pie? That's an easy concept, really. Think about that one. And then the last one is a segment. That's that part in there, the shaded part. And I think you can probably see that's an unusual shape. And how do we find the areas of unusual shapes? Well, it's usually one area, one known shape, minus another. I'll leave you to think about how you might get that shaded blue area, that segment, from two other known areas. Okay, we'll come back and look at that a bit later on. All right, let's go down now and have a look at trying to handle this first problem, which is gone past it there now, so we'll just go back up. This first problem, which is finding the area of a triangle where we don't know the height. So okay, let's start off with the friendly thing. If we did know the height, it would just be a half base A times the height. A here is the whole length of this side opposite big angle A. So that'd be okay. Let's see if we can get a formula for this H then, so we don't have to know that actual height. So let's look in the triangle ADC. We look in there, we see it's right angle because we've drawn the altitude. The side opposite C is H, so the sine of C is H over opposite over hypotenuse. Oh, we've just done it. We've found an expression for that altitude or the height H without actually having to measure it, just by knowing B and little b and angle C. What if come over here. What if the altitude in this obtuse angle triangle lie outside of the triangle? Would it still work? Let's see. If this is angle C, this is 180 take C, some angles on a straight line, and now in this triangle ACD, ADC, there, we've got the same thing. The sine of this angle is the opposite over the hypotenuse, so H is B sine 180 take C. But do you remember from the work on the unit circle, the sine of 180 take C is just equal to the sine of C. Let's revise that. Let's take this part of the unit circle and we're going to draw the axes in, and if that angle is C, let's say in there, what is it? The sine is the y coordinate of that point moving around the arc. And if we construct a congruent triangle over here, and this is angle C in here, and it's got a y and an x, the x is going to be negative now, going the opposite direction on the x-axis, but the y's are going to be the same. What is this angle now around there? It's 180 take C. So when you go that far around, the point on the arc of the circle has the same y value. It has the same c, has the same sign of c here, same sign. All right. So what we just investigated and proven here is that you don't need to draw in the height or altitude of a triangle if it's not there. You can use trigonometry, and the answer to the height of that triangle is b sine c. Let's have a look at the area then. Area is half the base, which was a, times the height, which was b sine c. So there's our new formula. If you knew sides A and B and angle C, you could work it out without drawing in and without calculating the height directly. What if you didn't know A and B and C? Could you do it with other sides? Let's come down, and the answer, of course, is yes. Because let's do another triangle. If we did, this one was A, B, C, we could do the altitude down here. And then we would have what? We'd be using that side, something like that, and B, and the formula would come to this one down here, isn't it? BC sine A, yeah, that one. So depending on where you draw the altitude, you're going to get different arrangements of sides and angles. And the other one, of course, is drawing it this way. Okay, from angle B down. Okay, well, okay, so let's have a look then at what that means. If you can use any of them. This is confusing. It seems to be a whole bundle of formula here. But what do they all follow? Here's what they follow. If you know two sides and the included angle, what are we doing? Okay, we're doing this, a half of the product of two sides and the sine of the included angle. This screen clipping is taken from Hayes and Harris publications, the Year 11 geometry book. Okay, so we need to do this, half the product of two sides and the sine of the included angle. It's quite often just written in this way, half AB sine angle C. But just keep in mind, it's not specific or unique to A, B and C. This is a generic relationship. It doesn't have to be A, B and C. It's important in maths to realise that some formulas are specific and unique. C, circumference is pi d. Can't play around with that. You've got to use C and D. But others like this are a generic statement. They don't mean you have to have A, B and angle C. They're trying to show you a pattern of half the product over here, half the product of two sides and a sine of the included angle. So be aware of that. Try to, if you like, verbalise all formulae in maths. You see whether they are a general pattern, a generic formula. Alright, let's go and do some problems. Let's have a look at what we can do. And this is really good, because we've got these two sides and the included angle, so we don't even have to draw an altitude now. You can find the area of a triangle without the base times height approach. So what is it in this one? Well, the side opposite C is 11, so it's a half AC sine B, isn't it? Because A, that's little a, this little b, and sorry, that's little c. You get that right, and we've got the angle B between them. So we can put down a formula. Always good to start with a formula, substitute it in and get a value. This is approximate because it's been rounded to 2 decimal places. Okay, and usually you put that in brackets. With the SACE course, 3 significant figures is more common, so you might also be able to do that, or hope you can do that. Alright, let's go and let you loose on some problems now. So here are some good ones. We've got 7 of them, there's 6 there. I'll bring up the other one in a minute. So pause the presentation, I'll show you the answers down below. But let's look at 7 first. There's 7, 7's got a pentagon, let's see the whole thing. Okay, so let's now look at the answers to that. There we have it, very nice. Check your answers, go back and see if you made any mistakes there. Alright, let's move on What else can we do with that formula? Well, here's an interesting problem. A triangle has sides of length 10 and 11 and an area of 50. Show that the included angle may take two different sizes. Okay, so let the angle be theta. So it's a half the product of the two sides. Sine of the included angle is 50. Okay. So you could put the formula up to start with, a half AB sine angle C. Okay, being that generic statement, taking it as a generic statement now. So multiplying these together, you get 55 sine theta is 50. Sine of 50 is 50 over 55. So the angle is inverse sine from the calculator. Make sure your calculator is set up in degrees, and you get 65.4. That's three significant figures that time. Okay, but just remember 180 takes 65.4. There's an angle, remember, just did it up there in the second quadrant. If this is 65.4, the sine is the y value, and there's a matching point over here making congruent triangles. That would be 65.4. So the actual angle to get around there is 180 take 65.4. So those 2 points will have the same sine, the same y values. So that could be either an acute angle or an obtuse angle triangle to have that area. Okay, that's what we're saying. So you might try to draw those two with the sides around it. Shall we do that? Okay, 65.4 is that, and this is, let's say, 11 centimetres, 10 centimetres, that's 65.4. Or it could be an obtuse angle. So that's a bit long there. So this could be 10, again, 11 and 10. And this time it would be 114.6 degrees. So that's what we're talking about. And the areas of those different shapes would be both 50. This is a long, skinnier one, if you like. Okay, that's the idea. Try and get some geometry going in your head there. So there are two angles. Alright, let's go down and give you a go. A couple of problems there. Question 8 and 9. 9's marked in blue here as being a more challenging question. Okay, so have a go and let's have a look at the answers then. Okay, answers are there. Alright, there is another way of finding the area of a triangle, and here it is here. Now this one we can't prove yet because we need some other maths we're going to do in the next presentation, the final presentation on this geometry. But Heron found it. He was an Egyptian, 1st century after the birth of Christ. He established a formula to find the area of a triangle in which all three sides are known and no angle. Oh, that's a beauty. So if we know these three sides, we can find the area. That's unbelievable, isn't it? And his formula is this. The area is the square root of S by S take one side, S take the other side, S take the other side. And what's S? The mean length of the three sides. Add the three sides up. No, not the mean, sorry. Add the three sides up divided by 2. It's actually called the semi-perimeter. Half of the distance right around the outside. A plus B plus C will be the perimeter, and you want half of it. So you've got to work that out first, and then put it into this formula. Where did all that come from? Well, it's based on the cosine rule, and we've got to establish that, as I said, next time. So we can't actually prove that to you yet. We've got to teach the cosine rule first. Alright, let's see if we can use that. That's very handy. We don't need to have any angles at all, so that's why it's so handy. Here we are. There's our example. Just got three sides. You obviously got to find the semi-perimeter first. That's adding them all up. That's perimeter around the outside divided by 2. So let's do that. 5 plus 6 plus 7 divided by 2 is 9. Then the area is that semi-perimeter times by that semi-perimeter minus one side minus the other side minus the other side. And there we have an answer. and that's to 2 decimal places. Okay, do you get it? Well, it's just a basic rule now, and you could say you've got to do a bit of monkey see, monkey do. Monkeys tend to copy each other, and all you can do at the moment is copy that formula down. You don't have the background to prove it yet, but we will give you that later on. Okay, let's go and see if you can do some now. Find the area of the right angle triangle. I've shown you the answer here. No, that's not good, so maybe just come up here. Find the area of the right angle triangle, those sides without using Heron's formula and using Heron's formula, and see what you come up with. You have to, how are you going to work it out without Heron's formula? That'll be an interesting one. Find the area of a triangle with sides of length those, okay, and then in question 12, see what you come up with. Okay, have a look at the answers. I think they've only given us the answers to 12 here. Alright, okay, so there we go. That's a tricky one in number 12. Alright, let's move on to sectors and segments. And as we said before, the sector is a piece of pie, if you like. The segment is a piece of the circles cut off by a chord. A chord is any line joining 2 points on the circumference there. Okay, so I've got a centre, a radius and all that. That's a segment. So I want to come over here and say to you, okay, that's a segment there. Okay, piece cut off by the line joining 2 points on the circumference. But let's have a look at that, and let's see how you might think about getting its area from what I said before. How do you think you would actually do it? Let's have a look here. We could take the whole sector, that's right around there. We could take the whole sector and then take away the area of this triangle in here. That would give it to us, wouldn't it? The segment, the area would be the sector minus that triangle. If we could work that out, that'd be good. Well, what should we do first? Well, we better try to do the sector. We can work out the triangle even when it hasn't got a 90 in it, this triangle in here. Alright, we can work that out. If we went to this unusual shape of the segment by taking the sector minus that other known shape, a standard technique, that would work. So let's go off and find the area of a sector. Let's see if we can do that. Okay, I gave you a hint earlier. We need to find what fraction of the circle it is. So let's come down here. What fraction of the circle is that sector? Okay, well, there's a clue. It's only got an angle there, a part of a revolution of theta degrees. Let's do some playing around here. If theta was 90, you would have a quarter of a circle, wouldn't you? Like that. Theta is 90 would be a quarter of a circle. If theta was 180 degrees, right around there, everybody knows that's half a circle. But how are we working it out? We're working it out by taking a fraction of 360, aren't we? So if the whole circle's got a revolution of 360, the fraction you've got is theta 3/60ths. So that's a fraction of the area of the circle you've got. So it's a fairly straightforward formula. And you're thinking of it as fraction of a revolution, or of a circle, fraction of a rev, let's put a rev, because you know a revolution is 360 degrees. Find out what part of that you've got, and that's what part of the area of the circle you've got. So you could have worked that out for yourself, I think. Okay, the area of a circle was the starting point, and we want a fraction of it. We can do the same thing if we want to find the part of the arc there that we've got. The arc length is the same fraction of the circumference of a circle. That's the circumference of the circle. So we can work out what part we've gone around the outside, if you like. This is called the arc length. We can find that distance as the same fraction, theta 3/60ths, of the whole circumference, which is 2 pi r. So it's driven by fraction of a revolution, this idea. Fraction of a revolution in sector work. Fraction of 360 degrees. So just keep thinking simply. It's good if you can write these formulas down and plug into them in copy or monkey fashion, if you like. But hey, wouldn't it be nice to understand up here how it works? And that's all it is. It's saying whether we're looking at the arc length or the area of that sector, then it's a certain fraction of either a fraction of a revolution times either the circumference or the total area of the circle. Do you get it? Okay, write down the formula so you've got it handy by there. Let's go down and have a look at an example. Okay, sector has a radius 12 centimetres and an angle of 65. What does it look like? Okay, it looks like this. And this is 12. Find its arc length. Okay, we want its arc length, that length. So what fraction of the circle have we got? We've got 65 3/60ths, there it is there. And therefore the arc length is that fraction of the circumference, and therefore it's that fraction of 2 pi by r, and there we have it. So we can find that. Can we find the area of the whole thing? Okay, well let's just check that out now, the area of the whole thing. A little bit of a glitch there, so let's keep going. So the area is the same fraction of the area of the circle, so it's 65 out of 360 times pi r squared. So this fraction idea to get the arc length or the area is important. What fraction of a circle or of a revolution have I got? When we say revolution, you think of 360 degrees, so that's a good way of thinking about it. Okay, are you ready to have a go? Have a go at some down here. Okay, so here we are, question 1, 2 and 3. Write down your formula and plug it in there. Let's have a look at the answers now. There are the answers, check them off. Okay, keep your thinking straight there of how all this works. Right, let's go down and have a look at just a little bit more now. Here, a sector has a radius of 8.2 and a arc length of 13.3. So it's looking a bit different now. We don't know its theta, radius 8.2 centimetres, and this is 13.3. So what's the formula? The arc length is this fraction of the circumference. So let's put the numbers in. So they've changed it around. They put the arc length on the other side. It's 13.3. Theta over 360 is 2 pi r. And then we'll put the numbers in and multiply both sides by 360, then divide by those numbers. So theta is approximately 92.93 degrees, and that's 2 decimal places. We've rounded off with the approximate sign. You can use that sign or that sign there. Okay, so that's another way of working backwards and finding an angle that would give you that arc length as that portion of the, or that fraction of the whole circumference. Okay, let's go down. Find the angle of a sector, of radius that, etc. Okay, so we'll just try and get, we'll go 4 and 5, pause it, have a go. And we'll go down now to 6. Yeah, 6 is an interesting one. 7, I told you about before, you're looking for the segment and they take you by the hand. Find the area of the triangle, find the area of the sector, and we've discussed how you would use those two to get the segment. So you have to do that now because we can find the area of the sector and the triangle. So have a go at those two, 6 and 7. Okay, let's go down now to 8, 9 and 10. Hang on, I've gone just a little bit far there. Let's just go up a little bit. 8, 9 and 10. 9 and 10 have got a coloured band, so they're harder. Okay, the pulley system's an interesting one. Alright, have a go. I'm going to show the answers now. So there are some answers for you. Alright, how's your geometry coming along? You're getting a fair few tools together now, aren't you? It's quite powerful. So we've just got one presentation to do, and that is where we're working in a non-right angle triangle to find sides and angles. So can we do without that 90 degrees? Okay, I'll catch you then. Cheers for now.